All right, here's the first problem from chapter 2. There's two parts to it. In the first part, in part A, here, so I'll do this part A right here. Part A, we know that the speed of light is equal to the distance divided by time. All right, so any velocity is distance divided by time. The speed of light is a very special velocity. And oh, this doesn't look right. So this should actually, yeah, that didn't. When I pasted this didn't come out right. So this it should actually look like this. It's 3 × 10⁻⁵ kilometers per second. All right, so that's and very often we'll write the speed of light like this. Right, so here's what c is. So here's another way of writing it: 3e5. All right, so in fact that's how Blackboard is interprets writing something in scientific notation. All right, so we'll see how to enter this in our calculator in just a moment. So E5, and the units are kilometers per second. All right, so this is the speed of light. All things that are forms of different forms of electromagnetic radiation, like visible light, infrared, gamma rays, X-rays, all of them, radio waves travel at the speed of light, including radar, as it's stated in this problem. Sorry. All right. So in this problem, we have a radar beam that leaves Earth. All right. So if this is the Earth, the radar beam goes out into space, and let's see. Let me see if I can draw a better comet. I tried this earlier. So let's say that's not a very good looking comet. All right. So this is my comet. All right, so there's a comet, and the radar beam encounters the comet, and then this is the distance to the comet. All right, so I'll do it like this. So this is d. All right, so this is what d is, and that's really what we want to know. All right, but they give us the round trip time. So the radar hits the comet, and then it bounces back. All right, that's the kind of a nice, wonderful thing about radar is it will bounce back. All right, so the time here it's really half the time that we're interested in because it's the round trip time. If I only want to know what the distance to the comet is, it's going to be 10 minutes. All right, so let's use MIN for minutes. We reserve a little m for meters. And we divide that by 2, right? Because it's the round trip time, right? So this is, of course, just 5 minutes, all right? So it takes the electromagnetic radiation 5 minutes to go out to the comet, to cover the distance. And by the way, this speed, 3 × 10⁵ kilometers per second, also, which is also 3 × 10⁸ meters per second if we did it in meters. That's the fastest that anything can travel in the universe. As all the different measurements we've made over the past almost 150 years now, that shows that that's the ultimate speed in the universe. All right, so let's figure this out in seconds. All right, because we have the speed of light in kilometers per second. Let's convert this. So I know that in 1 minute, right? In 1 minute, of course, there are 60 seconds, right? So the minutes cancel, and so 5 times 60 is going to give us 300 seconds, right? So it takes 300 seconds for the radar beam to go all the way to the comet, right? And that's all we are interested in. We just want to know what that distance is. So if we have this equation, d over t, well, we know what t is now, so it's d over 300 seconds equals the speed of light, which is 3 × 10⁵ kilometers per second. right? So if I multiply both sides by 300 seconds, I can solve for the distance, all right? So the distance is going to equal 300 seconds. That's supposed to be 300 seconds times the speed of light, which is always 3 times 10 to the fifth. Well, sometimes you're going to use 3 times 10 to the eighth. In this particular case, we want to know what the answer is. They ask us what's the distance to the comet in kilometers, right here it says do it in kilometers. So that's kilometers per second. So it's easier to just to do this calculation in kilometers per second. So the seconds cancel as they should. And so if I multiply, so let me get my calculator now. 300 times the speed of light. All right. So let me get my calculator. All right. So here I've already done this one, but let me just do it again with you. All right. So we got to learn how to enter scientific notation. All right. So here we go. So it's going to be 300 seconds times. So 3 times 10 to the fifth. So here's the thing. 3 times 10 to the fifth, you never hit times, you never hit 10 in your calculator, all right? I want everybody to understand that. That's actually really important to know how to enter scientific notation on your calculator. All right, so I'm going to do it right now. So with this particular calculator, I use the EXP button. That's pretty typical for a Casio type calculator. If you have a Texas Instrument calculator, there's an EE button. It's usually 2 capital E's. And usually with Texas Instruments, you have to hit like a second button as well to get to the EE. All right, so it's going to be 3. Remember, you're not hitting times, you're not hitting 10. EXP in this particular case, or EE, to the fifth. All right, so 300 times 10 to the 300 times 3 times 10 to the fifth gives us 90 million. So it's 90 million kilometers. All right, so let's write that in scientific notation and get a little more practice. And so I'm going to go one place past the decimal. All right, and so what I mean by that in scientific notation, that would be 9.0. All right, so let's take a look at where'd my calculator go? Okay, so let's take a look at this. So the decimal point is implied after to the right, right? The 0 on the right. These are commas right here. So it's going to be 1, 2, 3, 4, 5, 6, 7. So it's going to be 9.0 times 10. So you're going to write it. You could write it like this: times 10 to the 7th kilometers. All right, or which I like to do much more frequently is going to be 9.0 E7 kilometers. Right, these two things mean the same thing. All right, please remember that. All right, so now what we're going to do is if we read the rest of the part B to this problem, it says if the angular size of the comet is observed from Earth is 0.02 arc minutes and 0.43 arc seconds. All right, so that's a really tiny angle. I want everybody to understand what is the actual size or the diameter of this comet. All right, so what would be the size of this comet? And so we have an equation for that. But you got to know the distance to the comet, and we know that now. In kilometers, it's 9 times 10 to the 7th. Okay, so you need to know that, and you need to know what this angle is. We have to convert this angle to degrees. All right, so this is one angle. It's in arc minutes and arc seconds, but we're gonna do a quick conversion and convert it into degrees. All right, so I'll start there. So we're going to continue this problem for part B. So we know the distance for part A. This is the angle, although it's not in the right units. We got to get that in the right units. The right units meaning theta, the angle, the angular size of the object, has to be in degrees. All right, that's the way the formula is set up. All right, so and it's this formula right here. So the actual size of the object, that's just a script L. The actual size of the object is pi, right, divided by 180 degrees, right? That's what the pi divided by 180 times the distance to the object times theta. All right, so what we're going to do is we're going to convert theta into degrees, right? Because the degrees of the 180 and theta's degrees have to cancel. All right, so let's do that now. We'll do that part. So theta is equal to so remember, this is like a compound, but a very, very small angle. All right, so it's a compound angle. All right, so because it's made of arc minutes and arc seconds. All right, so it's going to be 0.02 arc minutes and 0.43 arc seconds. All right, so to convert this, it's actually pretty simple. I know that there are 60 arc minutes in 1 degree. That's supposed to be a degree. All right, and then I know that there are, of course, again, 60. It's 60 squared. So let me just prove that. So arc seconds, that's 2 hash marks. Arc seconds in 1 arc minute, and then there are 60 arc minutes in 1 degree. All right, so this is all you do. You just say 0.02 divided by 60 plus 0.43 divided by 60 squared. All right, so that's going to be our angle, and then we're going to use that right here for theta. All right, so let's see what that turns out to be. All right, because I'm starting to run out of time here. All right, so there's the 90. I'll use that in just a little bit. So it's going to be 0.02 divided by 60 plus, all right, so it's a very small number, 0.43 divided by 60 squared. All right, so this is, a very small fraction of so it's it's 4.53, if you will, if you rounded it to 2 places past the decimal, times 10 to the minus 4th. So it's 4.53 times 10 to the minus 4th degrees. All right, degrees. I could use the little symbol. All right, so now that's already my calculator. I don't really have to round that. So it's going to be pi. So this is the calculation for L. Pi divided by 180. Right, pi divided by 180 times the distance, which turned out to be 9.0. Times 10 to the 7th kilometers, right? And then times this really tiny angle, which this is the approximate value, 4.53 times 10 to the minus 4th, right? And it's in degrees, which it needs to be. All right, so let's calculate what that is, and this is going to give us the size of the comet in kilometers. All right, I got to stop talking and actually do some calculating. All right, so there's the angle. It doesn't matter what order I do this in. So times, where's my pi? There's pi, and then times 9 times 10 to the 7th, and then finally we're going to divide by 180. All right, divided by 180. All right, so there it is. And so this comet turns out to be, so we're going to just round it to 1 place past the decimal, 711.2. 711.2 kilometers. All right, and on the test on Blackboard on part B, you just would write in 711.2. And I would say, round it to 1 place past the decimal. All right, that's it for this video.